Surprised we're going back to law of sines? Remember law of sines? Law of sines. Right. So let me remind you of law of sine and think about why. Yeah, why is it doing that again? I thought we're done with that. Something like that. ABC could be an obtuse triangle, just represented a picture. These are labeled like little a and little b and little c like that, right? And there were these three quantities there magically equal to each other, right? Each quantity is a ratio of sine of that angle at vertex A divided by opposite side A, right? And sine B divided by opposite side, and sine C divided by opposite side. We can form these three ratios, and what happened? They're all equal to each other. For all triangles, it's magic. They're all equal to each other. And we never asked why, right? It's mathematics is science and numbers and geometry and things like that. You have to understand why on earth are these things exactly equal to each other. The idea was the area. Who remembers the area formula? 1/2. Here's lots of choices, right? Is the theta going to be down there at vertex A or vertex B and vertex C? So let's make a choice. If I'm looking at that angle A, what are the two adjacent sides? B and C, right? So an angle is sine A. That will be one formulation. But if I look at this angle right here, B, and that's actually different formulation, but would you agree that that's going to be the same area because it's the same triangle looking at a slightly different perspective, right? So if I do this with the angle at the B, what are the two adjacent sides? A and C, so you put A and C there, right? So do you agree these two things are equal to each other? I'm not setting it to you, I'm arguing these two quantities should be equal to each other. Why? Same triangle. Area must be the same, no matter how you look at it. So what is the third one? Vertex C gives you the two adjacent side AB and sine C. Is that right? So we understood why these three things are equal to each other. Now, that's one thing. Then we have 1/2 as a common occurrence here, so you can kind of cancel everywhere. Is that right? Then we're pretty good. We have sine and sine B and sine C showing up. Looks a lot like that. So we just have to kind of do something so that we get A and B and C in the denominator. So let me write down like this. BC sine A now is equal to AC sine B is equal to AB sine C. Right? After you knock down that common factor 1/2, this is what we get, right? Let's do something to the first term so that we get rid of BC and have A in the denominator. So what operation should we do to the all three quantities so that we get rid of BC? We divide, is that right? So we divide BC everywhere. We can't just divide that term, we have to divide all the terms involved in here to BC. Is that all right? So that first term looked like sine A alone, but we want to have A in the denominator, right? So let's put that A in there too. Then you have to put everywhere in A. Is that right? Then I pulled out, the first one is of course sine A over A. Something nice happened to the second part. It's C appears there and A appears there. Both of them appear, right? So they happen to be gone, and B is the only thing that survives. If you look at the third part, accidentally we knock down A there and B as well. So only C survives. So from that, all the cancellation, we have sine A divided by A, sine B divided by B, sine C divided by C. Boom. We have the law, right? Yeah. So if somebody asks you to on the street and grabs you, why is the law of science true? and you have to answer in one-liner, what would be the good reason? You have to just throw in one-liner. Why is the law of sine true? Guy in the street asked you. What do you say? Joshua. That's a good one-liner, don't you think? Area can be the same no matter how you look at it. And because of that, we have this law of sine, right? Good job. Guy in the